Hi guys, welcome back. So we've done a few videos on proof before. So this video today, what I really want to focus on is a more complex, familiar kind of example. So I had a few people that were asking me about this particular question today. So I want to go through and make sure that everyone is sort of on the same page for this. But first, before I actually do this proof by induction using that whole big process, that whole big method, I just kind of want to go through and explain why this is a more complex question. And really, it's a more complex question because we've got more complex notation. So I really want to explain to you what this notation actually represents first. So let's start off with a more simple example. We'll ignore this question for the minute and start off with a simple example. So if I had something along the lines, let's do a very simple series. So something like 1 plus 2 plus 3 plus all the way up to n. Then that's going to be equal to some function, right? I don't know what that particular function is, but it's going to be equal to some function. So what I might do, rather than writing out 1 plus 2 plus 3 all the way up to n, I'm actually going to replace this because this is a sum of expression. So I can write this as the sum of, and I'm going to write this as the sum of r all the way from 1 to n. So this r represents the whole 1 plus 2 plus 3 plus 4 plus all the way up to n. So it just saves me a little bit of writing, right? So let's go back and let's have a look at this example now. So the way that this particular notation works, if I was to do the sum of all the terms, well, the first term was, I've actually gone in, I've put in the values, and I've just found that the first term was equal to...
Sorry for the interruption. Attention to all staff, please. The staff meeting this afternoon will be now on Blackboard collaboration. Attention staff, the staff meeting this afternoon will now be on the Blackboard collaboration.
Okay, apologies, excuse me. Let's try that again, shall we? So I've substituted in the first term, so n is equal to 1, and then I've substituted in 2, then I've substituted in 3, and these are just the values that I got, so you can go ahead and substitute those values in. So the first term would be 1/3, the second term would be 1/3 plus 1/15, the third term would be 1/3 plus 1/15 plus 1 over 35, and we would keep going all the way up to the point of 1 over 2n take 1 times by 2n plus 1. And when I add all those terms up, this is the value that I'm expecting to get. So this is what we're trying to prove is true through proof by induction. So let's start off. Proof by induction, a little bit of a refresh. We're going to test the first case. Now for this case, the first case is 1 because we're looking at n as an element of all of the natural numbers. So 1, 2, 3, 4, 5, 6 all the way up to, infinity. Then we're going to test for any case. So we're going to assume that this is true. We can't actually prove that it's true. We're going to assume that it's true. And then we're going to use some algebraic information from this question, and we're going to substitute that into the next case, and we need to prove that that next case is true as well. And if we can do all of those three things, that means that we've proven this function is true by induction. All right, so let's start off. So what I'm going to do, I'm going to start off by proving to you that the first case is true. So I'm just going to substitute in my first term. So the first term is going to be 1 over 2 lots of 1 take 1 times by 2 lots of 1 plus 1. And I'm expecting that's going to be equal to 1 over 2 lots of 1 plus 1. So again, I've just substituted this back into that original expression. So I end up getting 1 over 3 is equal to 1 over 3. So the left-hand side is equal to the right-hand side, which means that this first case is true. All right, so let's do this, not the second case, sorry, the kth case. So let's substitute in n equals k to this particular expression. So what I'm going to end up with, I'm effectively going to end up with the same formula as before. I'm just going to replace all the n's that I see with k's. So we now have the sum of all of the values from 1 to k is going to be, the sum of all this function to to k, take 1 times by 2k plus 1, and I'm assuming that that's going to be equal to k over 2k plus 1. So that's just all substituted back into my original expression. And again, I'm going to assume that this is true. Now what I'm going to do is I'm going to try and use this information to help me prove that the next case or the following case is true. So what I'm going to do is I'm going to substitute in for n equals k plus 1. All right, so to do that, we're just going to do the same thing as before. Everywhere we see an n, we're going to substitute in k plus 1. So the sum of all the values from 1 to k plus 1, it should be equal to this. Now this is going to get a little crazy. So 2 lots of k plus 1, take away 1, multiplied by 2 lots of k plus 1, add 1. And then that should be equal to k plus 1 all over 2 lots of k plus 1 plus 1. All right, I'm going to go off screen and just quickly simplify a couple of these things. All right, so I've just gone ahead and I've simplified that just a little bit. Okay, so something that we need to understand about the way that this works, effectively what I've done is I've taken this previous term, I've added one more thing onto it, and then I should end up with this is my solution. So what I'm actually going to do, let's pick a different color. Let's do blue. I'm going to replace this, right? Now, all this is saying is I'm adding up all of the terms and the next term. Okay, so I'm going to rewrite this using this information here. Because this information here, I could write this as the sum of all of the previous terms to k is going to be equal to 1 over blah, 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 all this information here, plus the next term, which is this term here, and this replacement is the same value. It should be the same value at least, because I'm saying if I take the previous term and add the next term, I should still get this term here. Okay, so now what I can do, because I've written it in this particular manner, I can take this information here, right? Because I already know what the value for the sum of all the cases was. And that is equal to this case here. So I'm going to substitute this now in here. So k over 2k plus 1 plus the next term, 2k plus 1 over 2k plus 3, should be equal to this next solution here. All right, so that was a little bit crazy, but hopefully we can sort of see where I'm coming from there. Now, we managed to get to this point today in class, but I've been manipulating it and I've been mucking around with it, and I think that the best way that we can do this is by making this a fraction that all have the same denominator. I'm like the laziest person ever, honestly, truly, when it comes to mathematics, and I think that's something that makes me better at mathematics in a way, because I'm constantly looking for the easiest way to do things. I'm always looking for processes that simplify the amount of work that I have to do, okay? So I've tried a whole bunch of different ways, and this is the best way that I can get to do it. That does not mean that this is the only way, okay? So you may actually solve this using slightly different skills or slightly different algebraic method. If you can get the left-hand side to equal the right-hand side, that's all that really matters in this proof by induction thing. So you do not have to do this bit this way, but this is the best way that I've figured out how to do it. So I'm going to make all these denominators the same so that they are all like fractions, and then I can just add them like I could normally with a like fraction. So to do that, I'm going to multiply this to form an equivalent fraction. So this denominator here, 2k plus 1, I can already see here. So I'm just going to multiply this side and this side by 2k plus 3. And that's going to give me 2k plus 3 over 2k plus 1 multiplied by 2k plus 3. So these two elements, or these two terms, sorry, these now have the same denominator. So that's good. That means that I can add them because they're like terms. Now I'm going to do the same thing with this one. Now for this one, we've already got 2k plus 3, so I'm going to multiply everything by 2k plus 1, and that's going to give me this value here over 2k plus 1 times by 2k plus 3. All right, so now all these denominators are the same. So this is where I'm going to get a little bit lazy, right? I want to cancel as much as I can. I shouldn't say that. I want to rearrange to simplify as much as I can or whatever. So to do that, I'm going to multiply this entire expression by this bottom denominator. And that's just going to cancel that term there, cancel that term there, and cancel that term there. Okay, because when you do something to one side of the equation, you have to do it to every single term on that side of the equation. Okay, and because I'm doing that to this side of the equation, I need to do it to this side of the equation as well. So that's going to leave me with this really simple problem now to solve. So I'm going to expand on these brackets. So I'm going to end up with 2k squared plus 3k plus 1 is going to be equal to 2k squared plus k times 1 is k, 1 times 2k is 2k plus 1. All right, so I'm going to go ahead and collect my like terms now. So 2k squared plus 3k plus 1 should be equal to 2k squared plus 3k plus 1. Awesome. So the left-hand side equals the right-hand side. So let's just do a quick little summary of what I was just able to show there. So I showed to you guys that this first case was true. Then I assumed that this second case was true. Then I used the information from this and I substituted some values from this into this next case, and then doing that I was able to prove that that was true as well. So that means, therefore, our proposition is true by proof of induction. Sorry, very slow writer. Okay, so this is a question that took me about 10 or 11 minutes to do. And I've done that using a lot of explanation. But I really want you to think, like when you get to your exam, if you were doing a 60-minute exam, every single exam that you do is going to have a breakdown of 60% simple familiar, 20% complex familiar, and 20% complex unfamiliar. So generally what that means is you're only going to have 1 or 2 complex familiar questions. And that's not always guaranteed that it's going to be on a topic like proof. So if you guys have some other complex familiar questions that you want me to go through for your exam, then please just send me through like the page and the question, or if you have something from online that you want to send me, please just send it through and I'll have a go and do a video for you. If you still want some more stuff on proof by induction and you haven't gone and checked out my other videos, I would suggest going and having a look at those ones, because the previous 2 videos that I've worked on have been more simple examples, including proof by induction and proof by divisibility. And if you are still finding it a little bit confusing, then just email me and maybe I'll be able to do like a maybe in-depth, really back to basics video for you about proof by induction. But I know that there's a whole bunch of really fantastic videos out there already. Someone that I really like, I like Khan Academy and I like Eddie Wu. And I really like Eddie Wu because, like, he is an actual teacher in an actual classroom and he just films himself talking, doing his classes. And he really does have a deep background knowledge on this type of content. The other person that I kind of like for specialist maths content is Nancy Pye. And this one was one that was actually recommended to me by Mr. Doon. So I'll just write that. So Nancy Pye. So she's really good too. And there was a link that I sent you guys in one of the courses on eLearn, if we're able to access that within, this century sometime. So I have sent you a link, and it's some dude, I can't remember his name off the top of my head now, but he has literally like every single specialist video possible that he's made. So there is a heap of stuff out there and available. So if you don't like the way that I've gone through and done it, please, 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 please go out and seek out some other information. Alrighty, so I'm going to pop a couple more videos up. The other topics that I've had some requests for, I had a list. Where did that list go? I think the questions that I had were Gaussian elimination, so I'm going to do an example with that. Some more stuff on complex numbers, because that was what was cut off at the end of last term. I'm going to have a refresh or review of stuff on projectile motion as well. So if you have any other topics that you want me to cover for your exam, just let me know. Alrighty guys, I'm going to leave it there. I'll talk to you soon. Enjoy the rest of your Tuesday. Happy days. See you later.